Okay, now we are going to go over activation energy. And I have this reaction coordinate on the board because I want to go over with you how to read one of these and how to analyze it. All right, so first of all, the activation energy is the energy required to initiate a chemical reaction. And so the way that you read one of these diagrams is, if you look over on the left, we have the energy, which would be the this is the energy in kilojoules along the y-axis, and then reaction coordinate is along the x-axis, which is just the reaction moving forward. All right. So when we look at what I have drawn up here, I have drawn exactly the same thing. Well, not even. Let me see. I may have done not quite exactly the same thing as what's in the book. On page 428, it's the reaction coordinate at the bottom of the page. Now, what this tells us, if we're looking at a diagram like this, all right, we have the reaction is starting. Okay, the reaction is starting, and once it starts moving up in energy, once it gets to the top of the hill, then the distance between where it started and the top of the hill is the activation energy. All right, so what you know from a reaction moving forward is, obviously, when you're looking at a graph like this, the smaller the activation energy, right, the more spontaneous the reaction is going to be, the less energy is required to get it going. All right, but nonetheless, the top of the hill, the difference between the top of the hill and the energy level that it started at is the activation energy. All right, so as the reaction continues to go, all right, it'll even out. Now, the difference between where it started, which would be the reactants, and where it ended, which would be the products, right? This is when everything in the reaction is just reactants. It hasn't started yet. This is when the reaction starts to happen, and it gets to where all of the reactants are used up, and now all we have is products. Okay, so the difference between our energy at the reactants and our energy at the products is our delta H. That's our delta H, our difference in potential energy. So what this tells us in this particular graph, since the product side is lower than the reactant side, is our delta H is going to be negative, right? Because our delta H is going to be our products minus our reactants. So if we'll just say it's 300. It's a little bit higher than 300, but we'll just say 300. So we have 300 kilojoules, okay, minus our product, or our reactants is going to be minus 500 kilojoules. All right. So our delta H for this reaction is going to be minus 200 kilojoules. Okay. So that means it's going to be exothermic, right? It released energy. Now, with that being said, if you're looking at this and you're not given all this information, all right, if we don't tell you that this is the delta H and that this is the activate, well, so first of all, before I erase all of this, okay, if this is the way you calculate the activation energy, then it's just the difference between here, the top of the hill, and the bottom of the hill. Okay, so the activation energy would be 800 kilojoules. Okay, so the activation energy would be 800 kilojoules, the top of it, minus where it started. Okay, that's where we start to make products. We're increasing energy. This is where products start to be made. So once we get to that point, we're making products and we're going over to the product side. So our activation energy would be 300 kilojoules, okay? And that's positive. It's the top of the hill minus where it started, okay? So that would be our activation energy. But if you're not given any of this information, if all we have is just the diagram, okay? We're not given anything else. What can we tell in general by looking at this diagram? Well, we can tell that the products are lower than the reactants. So delta H is going to be negative. All right, so that means it's going to be exothermic. And we can actually calculate, if nothing else is written up here, we can actually calculate delta H, and we can calculate the activation energy. Now, if we were to compare, what if we had a reaction that looked like it looked like that. All right. So what this tells us is our products actually have a higher energy than our reactants. Okay. So what that tells us is our reaction is going to be endothermic. All right. Because it requires more energy in the products than it did in the reactants. And so our delta H here is going to be, remember, it's products minus reactants. So we're up at 500 kilojoules minus our reactants is going to be minus 300 kilojoules. So this reaction is actually going to be endothermic because the delta H was positive. So write this in your notes, or just remember this distinction. Positive delta H means that your diagram is going to look like this. Your products are going to be higher than your reactants. And it also means that it's going to be endothermic. Negative delta H means that your products are going to be lower on this diagram than your reactants, and you're going to be exothermic, or releasing energy. So be able to look at one of these diagrams and be able to tell what's going on. Again, the activation energy is calculated the same way. What this tells us is it's a big activation energy, right? Because it's still going to be the reactants subtracted from the top of the hill. So that's going to be 700 minus... So our activation energy is going to be 700 kilojoules, because we're at the top of the hill, minus 300 kilojoules, all right? And so our activation energy, we need 400 kilojoules of energy to even get this thing going, okay? So the steeper the hill, the more the activation energy is needed, all right? So I'm going to close out this video, and we will move on to the first law of thermodynamics, and the second.